Everyone, please accept my greetings and welcome. In our presentation, we will discuss the application of the differentiation in regard to the topic of related rates from Group 3, which we will be discussed in detail later. We are hoping that you will be understand what we are saying in our YouTube video. So, let's get to know each other. Alif Iqmal, also known as Fila, is the first of our teammates to appear in this set of slides, and his student ID is 201116045. The second person is Nur Aiman Zuhelmi, who goes by the nickname Aiman, and the student ID is 201105127. The third person is none other than myself, Nurin Adlina, and it is entirely up to you whether you address me as Nurin or Adlina. My student ID is 201117197. This is our group project for course MAT183, which is Calculus 1.
So in this presentation, we are going to discuss about application of differentiation under the topic related rates. So what is related rates, and more specifically, what is the application of differentiation? Well, differentiation and integration can help us solve many types of real-world problems. In differential calculus, related rates problem involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rate of change are known. What does that mean? The rate of change is usually with respect to time, because science and engineering often relate quantities to each other. The method of related rates have broad application in these fields. Differentiation with respect to time or one of the other variable requires application of chain rule, since most problems involve several variables. Now, the example of the said chain rule is as follows, where dy over dx equals to dy over du times du over dx, where dy over dx becomes the derivative of y with respect to x, dy over du becomes the derivative of y with respect to u, and du over dx being the derivative of u with respect to x. Now, there are two techniques to solving any problems regarding related rates. Number one, the procedure is to find an equation that relates to two quantities. Second, use the chain rule to differentiate both sides with respect to time.
We may proceed to the problem statement. The question is: James is filling an ice cream cone. The cone is 12 cm tall and has a radius of 4 cm. If the ice cream fills the cone, evaluate the rate of 1.5 cm cube per second. What is the rate of change of the height when the height is 5 cm? So the solution, we can take out known and unknown values and separate them into two boxes. Understanding what our known and unknown values tell us about the situation, our objective becomes finding any question that relate our given information. For the known box, we can have cone is 12 cm tall with a 4 cm radius. B prime equal to dv over dt, we will get 1.5 cm cube per second. So we still don't have the h prime equal to dh over dt minus the rate of change of the height over time when h equal to 5 cm. In this case, we will have the volume of a cone 1 over 3 pi r square height. Take the derivative of the volume equation with respect to time. Multiply each term by d over dt. From the formula, we will get d over dt volume equal to 1 over 3 pi r square height d over dt. And step 2, we can apply the product between r square and h while following the rule of implicit differentiation. dr over dt, or the value of radius when height is 5, is not provided, nor is it easily obtainable. We must analyze the cone further in order to find alternative solutions. We will get 2 over 3 pi r h dr over dt plus 1 over 3 pi r squared dh over dt. As you know, Sketch, when faced with related rate problems, just like now, it is sometimes helpful to sketch our problem. Here's the ice cream cone sketch with the info collected. Since our ice cream cone contain similar triangle, we can use the ratio r equal to 4 and h equal to 12. We just divide them to compare the cone radius and height. Um, Solving for radius, the radius formula is 1 over 3h. We can make the following substitution in our volume equation: 1 over 3 pi r squared h. We will get pi over 27 h squared, h cubed. Now that our volume equation has been simplified, let's try taking the derivative with respect to time. We can simplify the step one. We can multiply each term by d over dt from the simplified equation for the volume of a cone. We will get pi over 27 h multiply with h cubed multiply with d over dt. Step 2, we apply implicit differentiation. We derive with h cubed respect to height and multiply the result by dh over dt. We will get pi over 9 height square dh over dt. In step 2, we can substitute. Step 3, we can substitute our known value into the equation. We just input the dv over dt with 1.5 equal to pi over 9 and replace the height to 5 square dh over dt. Step 4, we simplify the equation to 3 over 2 equal to 225 pi over 9 dh over dt to make it easy to solve. And that is the final step we have to do. It is solve for dh over dt. We'll get 27 over 50 pi cm per second. Therefore, the change in height over time is 27 over 50 pi. 27 is the centimeter and 50 pi is the second when the height is 5 cm.
From this, we may conclude that the rate of change of the height is 20 over pi centimeter per second when the height is 5 cm. The equation volume of a cone and implicit differentiation theory can be used to arrive at this conclusion. In addition, sketching a diagram of our rate problems will help us solve it more effectively, as we demonstrated to you just now. It will be easier to get the solution if you know the procedures. So, do you guys think you can pull it now? This is our reference. And that's all from us. Thank you for watching.